Now it's time for you to try your hand at a problem that involves angular motion. And here's the example for you. We've got a disk that has a string wrapped around it, sort of like a yo-yo, and it's hanging with one end of the string held by some sort of a rod or a post or something. And we're simply going to release this disk and let it fall under the influence of gravity. But instead of just falling, it also has to unwind the string as well. So the question is, what is the acceleration of this disk as it's falling under gravity? So first, we'll work you through this problem, but first I'd like you to figure out what all the different forces are and then the corresponding torques that are acting on this disk. So pause this video and take a few minutes to do that, and then I'll check in with you. You should have found that the two forces acting here were the force of gravity, which is minus mg, and the force of the string, which is unknown to us. So those are the two forces that are acting on this. In terms of torques, only the force of the string is acting off-center to this body, so that's only one that's supplying a torque. Okay, so now what I want you to do is write down the equations of motion, that is the Newton's second law for both linear motion and angular motion, that will give us the motion of this body. So pause this video and write out the equivalent of F equals ma and the torque is equal to I alpha for this object. Okay, you should have found for the force, for the net force acting on this object, it is simply the force of the string minus mg, and this is equal to ma. And since the force of the string is acting opposite to gravity, it's going to make the net acceleration slower than g. In terms of the torque, we know that the torque is equal to the force times the distance away from the center of rotation. So in this case, it's r times the force of the string. But now there's a tricky part in here, and that is that this torque is causing this to try to turn in that direction, which is equivalent to it rolling downward. So this torque is actually causing an acceleration downward. For that reason, we're going to put a minus sign in there. And this is equal to I alpha. And I, for a disk, is mr squared over 2. And the acceleration relates to the angular acceleration by the factor of r, so we can write the angular acceleration as a divided by capital R. Okay, so now we have two equations, this one, and two unknowns, the force of the string and the acceleration. We don't really care about the force of the string, but we do want to find the acceleration. So now your task is to solve these two equations simultaneously to find the acceleration. So pause the video and go ahead and do that. Okay, let's work through this. First, we're going to rewrite the linear equation. And here, I'm going to notice that I have this minus r f of the string is equal to m r squared over 2a over r. You see that this r will cancel one of these r's, and now I have two r's on either side, so that will cancel this r. So I'm left with minus fs is equal to ma over 2. So I'm going to write that right over here. minus Fs is equal to ma over 2. Now, you can either substitute Fs into here, or you can take these two equations and simply add them to one another. Let's do the latter. That's particularly easy in this case. So the Fs's cancel, and we're left with minus mg is equal to 3 halves ma. We can cancel the m's, and we're left with acceleration is minus 2/3 g. Now, I want to point out that we had to be a little bit careful with that minus sign over there. If we had not done that, if we had gotten the wrong sign in there, we would have found an acceleration that was greater than g. But that wouldn't make any sense unless the string was actually pulling on this in a direction that was causing it to increase its acceleration rather than decreasing its acceleration. So that would have had to be a string that was somehow pulling downward.